Hello everyone and welcome to this workshop in which we will learn how to use the Python API for working in Earth Engine. And as an example, we will see how to perform a machine learning based classification. So if you are interested in my further work, you can check my website. And for all the contents and materials for these workshops are uploaded on this GitHub repository. So you can either scan this QR code or you can navigate to this website or here where you can find the samples, the codes, and yeah, all the details for these workshops. So overall, the workshop is divided into two broad sections. The first section will focus more on the brief introduction or overview of the background, or like the Python API or machine learning. And the later part will focus more on the practical coding section in Google Colab. So this is the overall agenda for today's workshop. And let's talk about the Python API. So in Earth Engine, we have the APIs through which we communicate. We have the processing clusters or servers, which process and analyze the data, and we have the databases. So conventionally, we request something or some processing through the API. It is processed in the Earth Engine servers, and based on our requests, the server assess data from databases, then processes, and then give us the output. So in this whole framework, the APIs plays a major role in communicating with the servers or for the analysis. So for APIs, we have two kind of main APIs for working with Earth Engine. Conventionally, we use the JavaScript API, and the second one is the Python API through which we can communicate. So this is the overview of both JavaScript and Python API and their frameworks in which they work. So if we see the JavaScript API, we have the conventional layout in which we have the code editor. On the right side, we have our console inspector task. On the left side, we have our script, docs, assets, and below we have our interactive maps. So overall, this is how we communicate with Earth Engine using the JavaScript API. But for the Python API, we can use any kind of IDE and environment, which I will talk about later in this workshop. So here, just like here is a Jupyter notebook in which each cell act as a separate code. So we run this cell from here to here and we get the output for this cell. So in this way, all the cells contribute to our analysis. So this workshop is more focused on Python, but the main question is why we are focusing so much on the Python. And the reason is that in recent years, Python has emerged as a powerful language with application in many different domains. So you might already be familiar with the data science concept that we can use Python for different type of things such as visualization, machine learning, deep learning, and so on. So in geospatial data science, we also use a programming language, preferably Python, for working with the location data such as shapefile, such as raster data, or so on. And in terms of integration of Python with Earth Engine, conventionally for the JavaScript API, we are just limited to the code editor stuff. But if we start working with Python, we have access to different kind of, you can say, tool. So here is a list of 4 categories. The first one is the automation. So we can just automate our simple task much more easily. So for example, if you want to export your NDVI collections for last 20 years, it is much more easier in Python to just use a for loop and just iterate for each year than it is on JavaScript. And for libraries, we have a large amount of libraries that are freely available in Python. Just to mention a few, we have TensorFlow, PyTorch, which are used for deep learning. We have scikit-learn, which is conventionally used for machine learning stuff. For data analysis, we have NumPy, we have SciPy, and different kind of libraries. Data visualization, we have Matplotlib, Seaborn, and so on. So these all the libraries which I named are freely available and you don't have to pay to access or work with them. And one more important thing is that for these libraries, we have a lot of documentation available. So a user don't need any kind of background knowledge in order to start working on them. There are a lot of basic tutorials that you can easily follow to start working with them. And next, we have the integration of cloud services with the Python API. It provides BigQuery, Dataflow, Beam, Vertex AI, and the integration of Google Cloud Storage. And lastly, the function that I use mostly on daily basis is the integration of development tools like GitHub, CI/CDs tools, and testing frameworks. So as an example of the Python API, I have included my journey of the 30-day map challenge. So last month I completed this map challenge, and you will be quite surprised to know that among all the maps and for the analysis, I used Earth Engine primarily for like 80 or 90% of the time, and for data generation, for analysis, and some maps for visualization. So here you can see the visualization time series map, and these all maps are created using the Python API of Earth Engine. Specifically, I use the Gmap and Cartoe package, and using these packages, I created the time series of these variables such as nitrogen dioxide, drought, or nighttime light. So if you are interested in this journey, you can scan this QR code, or you can navigate to this website over here to check the contents of my journey. And next, we have the difference between the syntax of the API. So syntax is basically how we write the code. So in JavaScript, we have our methods like .clip, .resample, and so on. And in Python, the syntax is mostly same, like all the methods are mostly same. There is just a little bit difference between the syntax, like how we initialize our dictionaries, how we do the functions and so on stuff. So these syntax difference I will talk later in the code session where we will start our code writing part. And here I have compiled a brief list of the resources. So if you are just starting your journey in the Python API, these resources will be very valuable for you. And using these, you can easily learn and start working on the Python API. So these includes a few Medium blogs, a Gmap documentation, and the official tutorial documentation available on the Earth Engine development resources. So each resource has the hyperlink, so you can easily click on each resource and you can check the contents. And before starting this, our course session, I would like to highlight a few things which you need to understand in order to start working with the Python API. So the first one is the environment. So for working with Python, we need an environment in which we can install our different modules, and then we can import and start working on our code. So there are two methods that we can follow. The first one is if we are working locally, like in our local computer, we can install the Conda or mini Conda, and then we can easily install packages. So if you are interested in this way, you can click on this link of tutorial and you can easily learn how to install mini Conda or Conda in your local computer. But for this workshop, we will focus more on the usage of Google Colab. So in Google Colab, we have already an environment, so we can easily install or import our packages and then directly start in working with them. A basic difference between Google Colab and other IDEs. So IDE is basically a code editor which we use for running and debugging our code. There are many type of IDEs which you can use like Visual Studio Code and the other. So these works locally, but the Google Colab is more built into your browser. So you can just navigate to their website and you can easily create a new Google Colab notebook and start working on it. And this is an overview of the Jupyter Notebook. So in Python, we have two type of codes. The first one is we have the conventional Python script ending with .py extension in which all the lines of codes acts as a one code. Jupyter Notebooks are hosted or run in the browser, so you don't need any additional software. You can just initialize the Jupyter Notebooks from Conda if you are working locally, or you can just open the Google Colab and the Jupyter Notebook will run. And let's talk about which type of packages we will be using for this workshop. So the primary package we will be using are Gmap, which is a package for working with the Earth Engine Python API, and the EE mount, which extend the further functions for the Earth Engine. So for example, in this workshop, we will use EE mount for evaluating normalized indices as well as for masking clouds and so on. But if you are further interested in local classification problems or local processing, you can use scikit-learn for machine learning classification or Rastrio. So if you are interested in this framework, I have by example of machine learning land use classification, which I will mention in the description. And let's talk about the machine learning part. So in machine learning, we have different kind of categories such as unsupervised classification, supervised classification, reinforcement learning, and so on. So for this workshop, we will focus more on the classification problem, specifically how we can differentiate different kind of classes using our labels. So as an example, you can see the land use land cover, where we can differentiate the classes based on their spectral response or characteristic. For example, the cropland, different cropland differs from the urban land or water and so on. So for classification, we have different type of models which are available both in Earth Engine and locally. So in Earth Engine, you can see the list of classifiers that are available ranging from random forest to SVM, to quart and decision trees and so on. But as you can see, this is a very limited list of classifiers that are available, and mostly we are working on some classifiers that might be suitable to some problems, such as if you want to use XGBoost or Live GBM classifiers, they are not natively available in Earth Engine. So in order to work with those model, you need to install scikit-learn. And here you have a large collections of model which you can use for any kind of machine learning problems, classification, regression, and so on. And lastly, for the workflow, this is the simplified version of the workflow that we will follow in the later code section. So in the start, we will create our features, which will include our satellite images and satellite images bands, including blue, green, red, near infrared, and so on. And then including our features such as spectral indices, or if you want to include any other such as elevation or slope or aspect, you can include those. And then we will create our labels, which include the properties or labels of land use land cover. Or in case you are performing any other classification such as floods, you can choose binary classification labels such as 1 for flood, 0 for non-flood. Or in case of land use land cover, you can choose label based on land use type, such as 1 for urban, 2 for vegetation, 3 for water, and so on. And then we will have our training classifier, which will train based on labels and features and then can predict the output. And lastly, we will do the accuracy assessment to assess how accurate our predictions are. So this whole workflow will be based on Google Earth Engine and the Python API. But if you're interested in more advanced classification frameworks such as the hybrid framework, you can follow this guide in which you can use Earth Engine to create your features and labels. And then you can convert those features and labels into numerical numpy array and then use that numpy array to train the classifier and then the accuracy assessment locally using the scikit-learn Python modules. And if you are interested in this workflow, you can navigate to my website. And here you can see the land use land cover by machine learning. You can click on it and it will navigate you to the medium block where I have written in details how you can start working where once you have the data set and do a classification locally in Python using scikit-learn and Rastrio. So that was all for the first part, and now we will jump into the code. So to open the code, you can either click on this link or you can navigate to the website of this project here. And here you can see the link which says open in Colab. So if you click on this link, it will open this Colab notebook. Okay, so now this is the Jupyter notebook in Google Colab in which we will work on our example of machine learning classification. So before starting the code, I assume that you have a basic understanding of the basic Python programming and then the JavaScript Google Earth Engine language. And if you don't know much about the Python programming language, I highly suggest you start some course from for the Python And if you have time, I highly suggest you complete the Harvard CS50 score so you can have a much more in-depth knowledge about the working of the Python API. And also, you can check out the Google for Education website for their tutorials and materials on the Python. And lastly, after learning the basic of Python, make sure you have practiced using the official documentation of Google, which you can find right here. Once you have learned the basics of Python, you can easily differentiate between the syntax differences, which we earlier talked about in our presentation. So here is an overview of the difference in syntax. I will just zoom in so you all can see. Okay, so the first, if we check the differences, all the basic things like defining a function is different in Python and different in JavaScript. And so is the declaration of variable. We have to insert var in JavaScript, but in Python we don't have to do this, and we can just call the name and just the variable. Yep. And all the logical operators, you have to take care that in case of JavaScript, we have the simple operators. But if you are working in Python, you need to capitalize the first word. Like for and, you have to write capital A and then others. And just like this, we have all the others. One key difference I want to highlight is the difference between the dictionaries. So in case of JavaScript, you don't need to write a dictionary key inside a string. So here you can see we have dictionary key into values. So in JavaScript, it will automatically understand that the first one, this is the key and this is the value. But in case of Python, if you have a declared value and or a variable, and you want to insert it as a key, then you need to insert it as a string, just like here. An example would be like if you want to visualize an image. So conventionally in Earth Engine, in JavaScript, we have like simple dictionaries where we define minimum and maximum and bands or palette. But in case of Python, you have to insert a string for each of the min, max, bands, or palette. I will show this in the later example. So once you have a clear understanding of the differences in syntax, then let's talk about the Jupyter Notebook in terms of Google Colab. So in Google Colab, when you open this, the first thing that you need to do is to connect. So when you click on connect, it will automatically allocate a runtime and will connect it into a virtual environment, which will give you a virtual processing CPU and GPU, depending upon the availability. And once you see it is connected, you can see that you have around 12 GB of RAM and around 100 GB of storage. Once connected, you can go to install packages. Now, recently, a Google Colab team has included Gmap inside the Google Colab, so you don't need to install it separately. So for this example, all we need to install is the EE mount package. So for install, we write this pip install and EE mount, and once you click on run, it will automatically install the required dependencies and this package. And now we can see the code has run. We have seen the green tick and shows it took around 12 seconds to install this package and all the dependencies for this package. And next we can proceed to install importing the package. Now installing the package is totally different from importing. So in installing, we install the package into our virtual environment, which is connected. Then we need to import all the packages we are going to use. So here I will use EE Gmap for working with the Earth Engine API, Gmap color maps to visualize images, GeoPandas to working with geodata frames, EE mount for normalized difference vegetation index or other indices, and for cloud mask, and lastly OS, which is a Python native module to work with file system files. And here you can see this code. So what this does is this initialize our session. So if you go over here, we just click on some code like hello world. And if we click it, so it gives us an output in the console. So we don't have to initialize it because it is already logged in with our account. But in case of Python, we need to initialize our environments so Earth Engine can understand that we have the access to our Earth Engine account. And in order to initialize, we also need to authenticate it. So this is the step you need to do only once. So therefore, we use a try initialize, and if this fails, we can first initialize our session and then initialize. So I will just run and show you what this means. So it will first quickly import all the packages into our environment and then it will initialize. So it says that we have to initialize it, and in order to initialize it will open a new window with our Google accounts in which we have to select the account and then allow the account to use our Earth Engine credentials into the notebook. So I will quickly sign in. In the next, we need to connect our Jupyter notebook with Google Drive because we need to access contents and we need to save contents into our Google Drive. Now, if you are working locally, you don't need to follow these steps. Instead, you can just copy and save your contents and outputs into your local folder. So here we will first import Drive from Google Colab and then we will mount our main folder. And then we need to specify the location for our working directory. So by default, in Google Drive, we have this location, My Drive and Collab notebooks. I will show you here. So this is the Collab notebook. And here using our location to make the directory. And then this command to change the directory to this location. And then finally, I am printing the current working directory. So let's run this code. And when you run the code, it will ask you to connect with Google Drive. And here we can see that the working directory is now Contents Drive, My Drive, Google Colab Notebooks, and GE by Machine Learning. So here we can see we have a new folder with the same name. So the next, for working with this machine learning example, we need to specify a location in which we can work on. So as an example, I'm using Lagos, Nigeria, point location, lat long, and assigning it as a geometry. And then I'm creating a buffer of around 5 kilometers. So I can use that buffer as a study area. So note here, if you are just using point dot buffer 5,000, it will mean it will create a buffer of around 5 kilometers around this point. But if you use the bound, it will use the rectangular boundary around that buffer. So in our case, we want to use the boundary instead of a buffer. So we will use the dot bound. And since we are using Gmap, so we will use the map.gmap.map, which will create an interactive map, and then we will center object and add layer. So if you want to know more details about the Gmap, you can navigate to its website. And here you can check all the materials related to Gmap, its codes and everything. Let's quickly run and visualize it. Every time you need to assess your interactive map, you need to write map since we have declared this variable as a gmap.map. So here we can see that our buffer rectangle is shown on the map. So in this way, you can import any raster or any shapefile, and then you can create a map instance, and then you can center objects same as the JavaScript API, and then add layer to that map. And just optionally, you have to write the map in order to visualize it. And just to clear, I will delete this map and just run. So if you don't write the map at the end of the code, it will still process all this information, but it will not visualize. So in this case, we want it to process and we will visualize it at the end. And next, we have our study area. So for the next, we need to define and filter our data for feature generation. So for feature, I am here using Sentinel-2 collection, specifically Sentinel-2 surface reflection data for 2023 and for the first 15 days of the first month. So here you can see I have defined sentinel-2 variable, and here is all the commands. So first is the sentinel-2 collection, then the filter date, same as the JavaScript API. As mentioned earlier, all the methods are similar to the JavaScript API. The main difference is, as you can see, I'm using the brackets and writing all this. Whereas in case of JavaScript, we don't need to put the brackets here. And the reason is that if you are using the same approach as the JavaScript, for example, as sentinel2 is equal to ee.image. And if you want to apply the filter, you need to do this in the JavaScript, like, right? But in case of Python, this is not correct. So if you are using this approach, you need to write this, and then it will read this as a method applied to this image. Or another way is the similar which I used here is you can just put a bracket and now it will work. So similarly, I have filtered and taken the images between the 15 days and then filtered them with our study area. And here you can see I have commented this code, which is this function, which masks the cloud. So instead of using this function for masking clouds, I am using mask cloud function from the modules named EE mount. So if you want to check more details, you can go to their website and you can easily check each function. So this is the website of EE mount. You can easily assess all the function you want. So for this workshop, I am using mask cloud, scale and offsets, and spectral indices functions from EE mount. So you can check their website for more details. And for spectral indices, I'm using modified normalized difference vegetation index, buildup index, and water indices. So if you want to include any other indices, you can search. And this function supports a large list of spectral indices, around 200 or 250 indices. So you can just write their names in it and it will evaluate the indices. And then I am taking the mean for the images in this range. And lastly, I am clipping all the final image which our study area. So with this, we have the final image that we can use further for processing. In this image, we have all the information that we will need further. But since we want to specify our bands, I will just filter the bands that I require. So I will need band 2, 3, 4, 5, 6, 7, 8, 11, 12, and 3 spectral indices. So I will declare a list and input all the bands that I will need. So, but if you want to check the name of the band, you can write sentinel2 dot band name, and it will give you a list of the bands available in the Sentinel-2 image. And next, we need to define a new image with all the bands. So this code will filter these bands from this final image. And here I have created a dictionary of the visualizing parameters. As I said earlier, the dictionary is quite similar, but in terms of key, we need to define the keys inside the string. So here you can see min, max, and bands are inside these strings. So this is a basic difference between the dictionaries in Python and in JavaScript API. And lastly, I have added all these new layers into our map. So the first layer is the false color composite layer, and then each of the indices. And in the last, I have also included false, which means do not show them by default. I will just quickly run this code. And now in the 5 seconds, it has calculated our image. So if I want to visualize it, I will insert and write map. And here you can see by default, there is nothing because we input the false into our map add layer, which will by default hide the layer. So you can go into this panel and here are all of the layers. So I will quickly visualize the false color composite. And this is our image, our NDVI, build our index, and water index. So in this way, you can prepare as many features as you want. You can import elevation similar to this, and at the end, you can add that elevation into Sentinel-2 as add bands. And inside this, you can enter the name of the image and it will be added as a band. So far we have created our features. And next, I want to create labels for our machine learning classification problem. And for labels, I will show you two methods. The first one is that you can use any reference layer and you can generate training samples from it. For example, we have the land use land cover dataset from eCity. And here we can see different classes of land cover. And to generate labels, we can generate labels and assign values of each pixel of the land use land cover. So if you want to know more about the eCity map and its detail, you can navigate to its website. I have included the link here. And in the code first, we will import the image collection in the same way as we did in for the case of Sentinel-2. We have imported the image collection, then filtered it. We are using the image for the year 2022 since it is available yearly. Then we will mosaic it to create a single image and then clip it to our area of interest. And optionally, we are remapping it to the number, continuous number, same as mentioned here. So you can click on this sample code and you can see this part of the code. And here are the dictionaries of names and colors of the land use land cover classes. In case if you want to visualize it and add a legend, it's just here. But in this workshop, we will not use it, but we can use it as a reference. So for this workshop, the first method example, we can do something simple. Like we want to classify our image into water and urban areas, or you can say water versus non-water. So for that, I want to convert this image into a binary image where one pixel will show water, whereas the other will show build-up area, since we are focusing on those two classes. So for that, I will create a new image called field, and I will remap the values. So here I am saying that change the values of the image where the image value is 1 to the image value 2 and the image value 5, which is a build up, to the image value 1 and rename it to LC. So the band name will be LC. So by this code, we will get the image where where the image pixel 1 will show the build up and the image pixel 2 will show the water pixels. And lastly, I'm adding this new image to our map. So quickly run this code. And just to confirm, we will again call the map. And here we can see we have our new eCity field in which we can see the red color shows the build-up areas from the land use land cover, whereas the blue color shows the water pixels. One important point before you proceed to the next step is you need to make sure the projection and scale of your labels and features are the same. In most of the cases, if you're working on multiple data sets, such as in the case of Sentinel-2 and elevation, they will have different projections and scales. So in this case, if you proceed, the result will not be accurate. So I will suggest you, if you had that case where the projections are different, you can reproject or rescale the images to the same scale before proceeding. So here, just to confirm, we can run this code and it will show that the image projection of our final feature has the same projection as of our reference data, which is our field. So once we have our features and labels prepared, we will create stratified samples. So in stratified samples, the samples will be created equally for each class, which is given. So here I have included a sample size of 1000 since we have very large field and seed, which will do a randomizer, which ensures that every time we run the code, the output will be same, and we specify the scale in which we are working. So in this case, we are working with Sentinel-2, and Sentinel-2 has a scale of 10, so 10. And we need to create samples based on our field. So in this case, our field was the newly created E3 E3 layer, which has two values, buildup and water. So here we have field, and then we create a stratified samples. And here we give number of points as 1000, class band as LC, because we rename our field to LC, and then region, which is area of interest, scale, projection. And here I have used dot projection to define this projection, and seed and last seed geometry. So the geometries ensures that the output sample contains the geometry information. And lastly, I have added these samples into our map. So when we run this code, we can see that 2000 of the total samples are created, because in our field has two classes. So 1000 multiplied 2, we have 2000 samples. So I have also printed the first sample to get the information, what kind of information is stored or for the samples generated. So the sample contains the information of geometry, because we mentioned the geometries to be true. And then we have the properties, which include the land cover type. So the land cover value is 1. This means for the first sample, the value is 1, which indicates it's for buildup. We can also type map and can see the samples, because we have added them into our map instance. And here you can see that we have these black circle samples created in our study area. So quickly delete it. Yeah. Once you have created your samples, you need to sample them with your features. So earlier we have created our Sentinel-2 images with, so we have a total of around 13 features, and now we need these features to be for each sample. So um, in this way, we want the final sample, a final point, to have the 13 values of each feature and its location and its label. So for that, I will use the sample region, which will sample each pixel based on the point. So as a reference image, I'm using the final image, then sample regions. And in the collection, I am mentioning the samples that we just created, properties and land cover, because these are the labels, scale as 10, and projection and geometries too. So once I run this and check the first point, we can now see the first point has all the properties of our features. So the point indicates the B12, all the bands values, as well as all the features values. So in this way, you can generate samples, and you can then sample your features for each point based on this. So here you can do an optional step. You can also export your training data sets to your Google Colab or your local drive. For that, you need to use the GMAP module, GMAP, because this is a Earth Engine object. You need to use GMAP EEE to shapefile, and you can mention the sample, and it will export your samples into your local drive or Google Drive. But here we want to use these samples to train the model. So the modeling part, before training, we need to divide our samples into two categories. So the first one, we need to divide it into training and then into testing. So we can test how is our model performing and how is the model accuracy. So as a split, I'm using 0.7, which indicates that 70% of the samples will be used for training, whereas 30% will be used for testing. And here I will generate a random column and then filter the samples. So the 70% samples will be stored as training, whereas 30% as testing. And then I will build a classifier and train it. So for classifier, I'm using the random forest classifier with the number of trees as 100, and then using .train to train this classifier using our training data sets, class property as LC, and input properties as bands because we have mentioned the bands names here. So we can use this list as the bands. And next, once our classifier is trained, we can use this classifier to classify the image. So we can mention the image, select bands, and then we can use classify methods to, and using classifier, we can classify the image. And lastly, we can visualize the classified image into our map. So let me run this code. And here we can see that our machine learning model has successfully classified our image into two categories. The red one is the buildup, whereas the blue one is the water. And in this way, you can use any reference data to train your model and to get the output. And once you get the output, you need to check the accuracy of the model to ensure that the model is performing well. So for accuracy, I'm using confusion metrics, overall accuracy, producers, and consumer accuracy. So here you can see that I'm using two categories as training and testing. So the training will check the accuracy for our trained classifier, whereas the test accuracy will use our testing sample and generate the accuracy of the classifier based on this testing data. So if you want to know more details about these accuracy metrics, you can navigate to my any of my paper and just navigate to the accuracy assessment section. And here you can find the details of the accuracy assessments, equations, and how you can evaluate them. And you can also check the visualization, how you can interpret these values. And you can get all the papers from my website. Just navigate to valigio.com, and here under publication sections you can find all my papers and their PDF. So as a reference, I am showing you my this paper for the wetlands classification in Sylhet, Bangladesh. So now we have our cell has run, and here we can see that the training accuracy is 1, which means 100. And similarly, our testing accuracy is 0.99, which shows that the model has classified the image into two classes with higher accuracy. But of course, in real world scenarios, the classification problems are quite complex, and usually the accuracy above 70 is reasonable. So this was all for the first method of how you can use our reference layer to generate your labels. But what if you don't have a reference layer and you want to generate your labels from interactive map? So for creating samples, conventionally in JavaScript, we have the map in which we use these tools to generate any type of geometry, polygon, or layer, and we insert its properties, etc. But in case of Python, the method is totally different. So I will show you how you can create the training samples from satellite images. So here you can see that we have our all previous layers, false color composite and spectral indices. So you need to go to this toolbox icon and you need to click on this plus, so it will expand all the tools. And here you can choose this collect training samples icon to start collecting your sample. So here we have three column: property, values, and colors. So for our samples, we need the property as LC because we previously input it. And then we need to define the value. So in case of land cover classification, the values we can start from 1. And here we can add a property such as class. And for the class name, we can write build up and click on apply. So it will create this property and layer. It will, so every sample that now we create will have the value of 1 and will be considered build up. So just to show you, I will navigate it to, you can enable the NDBI build-up index since we want to collect samples for build-up area. And you can select this tool and then you can draw a polygon like this. And your sample is collected as the value of 1. Similarly, you can collect as many samples for any class as you want. and you can change their colors to any color that you like. And once you have collected the sample for that one class, you need to go to another cell. You need to declare a variable, and you need to write map.userRare. So what this does, it will collect all the sample you have drawn onto the map and will store them into your vegetation variable. So just to check, we can go to our urban, and I will just print it to check that if our samples have collected. And yes, here you can see that in our map, we have three elements. And for each element, we have property as class builder and land cover one. So in this way, you can draw as many samples for as many classes as you want. But optionally, I will suggest you to go with a single class at a time. For example, in this case of build up, once you have drawn all the samples, you can go to the next code and you can enter this and click run the code. So it will store it. And then you can proceed to the next class. And the reason I am suggesting this is because if you change the value to something else, like I want to do it for vegetation, give a color green and click apply. So here you can see that the previous samples are deleted, and we can start working with our second features, which is the vegetation. And for vegetation, we can use the NDVI, and we can start collecting samples onto the areas which have higher vegetation. So let me collect a few samples here. And just to confirm for the vegetation, we can run the vegetation code, and it shows that it has collected two samples, and each sample will have the property vegetation and LC. So in this way, you can collect samples for individual class one by one. And just to save the time, I have already prepared the samples, which I will now import. But before that, once you have collected all the samples, you need to merge them into a single feature collection, because as you can see, each sample is itself a feature collection. Similar to JavaScript API, you need to merge all the samples into a single feature collection. And optionally, I will advise you to export these feature class to your geodata frame, so it will be much easier to work on in later. So optionally, I will suggest you to convert these samples into a shapefile and store it into your local computer. And for do that, you can convert the Earth Engine object into a geodata frame. So here is the final geodata frame. And then you can save this geodata frame to your Google Drive or your local file. So in our case, we have initialized this notebook into a Google Drive. We have provided the location previous. So we can save our samples to that drive. But in your case, you can do it locally or anywhere as you want. This is how you can save your samples as a shapefile into your local computer or your Google Drive. Now, just to save time, I have already created the samples and have stored them into a GeoJSON file. So if you navigate to this project GitHub repository, there you can find the samples folder. And in the samples folder, all the samples are in shapefile as well as in GeoJSON file. So now here I will enter the URL of the GeoJSON, and next I will give a name. So the GeoJSON will be stored in our working directory, and I will use the gmap function called download file, which will download this GeoJSON file and will store it into our default location. So here you can see this is our working folder, which is empty. And once I have run this code, it shows that it has stored. So we can check our drive folder. Yeah, here you can see that the sample GeoJSON file is now stored into our working directory. And next, I have read that file using GeoPandas and convert the GeoPandas into Earth Engine. You can optionally you can use the default function of Gmap to convert the GeoJSON into Earth Engine, but for me it was not working. So I am using the two-step approach, like converting the GeoJSON file into a geodata frame and then converting the geodata frame into the Earth engine. And lastly, I have printed the features. So for my samples, I have like 42 samples, and each sample has the same color, label, and line cover property. Now, once you have created the samples, you need to create the Now, once you have created the samples, we need to create the images for each sample. Just like our previous example in which we created, where it is, yeah. Just like the previous example in which we create the field which contains two classes, we need to create a field for our this example. So to create the field for each class, I am using this approach. So this approach create the image based on our feature and clip it for each of the sample. And then we can filter our image based on our samples. For example, for water, I am filtering based on the label water. And lastly, we can multiply it to its label value. So for example, here it will create the image with all the pixels value 1. This will clip the that image with our sample. This code will filter that samples only for water. And here I am multiplying all the pixel values with 1, and lastly renaming it to land cover and converting the image into an integer. So overall, it's a lot of information to digest, but this is how we create the field for each class. And we can do the similar thing for each class. So as an example, I'm using four classes: water, urban, vegetation, and barren. And to change the class value, I am multiplying each pixel by its value. So for urban, the value is 2, so multiply by 2. Vegetation 3, and similarly, barren 4. And lastly, to create the field, I am combining all these images into an image collection and then mosaic. So what it does, it will mosaic all the field, our individual class fields, into a one image field, which we can use later on for sampling. And next, all once we have created the field, all the remaining steps are quite same. So here we will again do a stratified sampling, but for this time I have reduced the sample size to 200. And the reason is that if you see here, we have like four classes, and 400 multiplied by 2 equals to 800. So this will create 800 samples of the total. And all the parameters are quite same. Instead, we are using the field, this field for sampling. And just quickly run this code. So here we can see we have now around 800 samples, and let's check the value of the first sample. So similar to the previous example, we have the coordinates, and then we have the property of land cover 1. And next we will sample our features into these samples. So in order to do that, we will use again sample regions, and everything will be same as the previous step. And when I will run this, so here we can see again we have our sample for each of the features bands, including the spectral indices, and land cover property is 1. And next, we will divide our samples into testing and training based on zero point 0.7 threshold. And then again, we will define a classifier, random forest, with the number of trees 100, and train it using our this data. And lastly, we can classify the image and then visualize it. So here you can see I have changed the parameter a bit, because previously we have two classes for our land use land cover, but now we have our four classes because we are using four kind of samples: water, urban, vegetation, and barren. So in this case, I have included the minimum one, maximum four, and assign a palette based on their properties. So blue for water, red for buildup, green for vegetation, and orange for barren land. And this is turned as, let's say, classify new. And yeah, just yeah. So let's run this. So these were the results of the previous classification, in which we use land cover of E3 as a reference and just use two classification, two class classification. And this is our new classification using our manual labels for this study area. So here you can see the most of the areas are urban around here, but our classifier has detected this as barren land. And this is because of the error in our sample. So a machine learning model works on the principle in which the good quality sample will result in good classification or output, and bad samples will result in bad output. It's like just like the principle of garbage in, garbage out. So you need to make sure the samples that you are collecting are of high quality, otherwise your map will not be so good. So in order to check the accuracy, we can again use these accuracy metrics. And here we can see that our training and test accuracy indicates that the classification results are quite good, which indeed are good. The class model's performance is good, but our samples quality has resulted into a classification that is not so reliable. So in this way, you can do classification with higher accuracy if you have a good training samples data, and you can check the model's performance from here. So in order to check the quality of samples, you can overlay the sample over your any feature. For example, here I'm using false color composite, and you can overlay the sample, and then you can go to the tool and you can use the inspector tool to check if the sample is correct or not. And from there, you can improve your samples and then perform again the classification using the same method. But overall, from the accuracy assessment, you can get an idea of the performance of the machine learning model. And in this case, we can see the model is predicting with high accuracy based on the labels. And once you have your reliable results, you can export the image to your local drive or computer. So first we will convert the image into a simplified form, which is using 2u integer 8. We are converting the image because our classification ranges from 1 to 4, and the u integer 8 has a range between 0 to 255. And then we can use the gmap to export the image. So here we can use gmap export image, and here we will mention our classification name, which is classification new. We can define a scale and region. So here, if I mention 10, it will give me an error because the pixels are outside of the limits of Earth Engine. This means you have to first export this image into your Google Drive using gmap ee export image to drive using this. So this will export your image into your Google Drive. But if you want to quickly get the image into your local computer, you can use the EE export image. So here I am using it with the scale 20 and click on run. So here it says that it has downloaded the classified image to our working directory as the name classified new. So we can just quickly go there and check if the image is there. Yes, the image is there. And next, as I mentioned earlier, you can use export image to drive to export this image into your Google Drive. Let's click this. And to check the progress of the task, you can use ee-task, and you can check the progress. So it states it has completed. So you can optionally go to Google, your Earth Engine code editor, and you can navigate to task. Here you can see that our recent export is in progress. So once it's complete, it will be available into your Google Drive folder. You can also download this file and visualize it. So I will just quickly visualize it into QGIS. So this is our image which we just exported, and I have opened it into the QGIS. I will quickly give them a symbology. So here is our final image which we have exported into our local computer. So in this way, you can easily do any kind of classification. You can build your model for flood classification. You can build model for prediction and anything you want. All you need is two data sets. The first one is a feature, which in our case was the Sentinel-2 image, this one. And the other feature, the other one is the labels that you want to train the models to predict similar to them. So in our case, the labels were city land use land cover in the first example, and in the second example, we have manually drawn our polygons or shapes. So this was all for today's workshop. And if you are interested in more advanced classification workflows, you can follow this guide, which I also mentioned in the our presentation part. So you can use a hybrid workflow in which you will use the Earth Engine to export the features and the labels. So here is a code to export individual bands into our Google Drive, and then you can export the samples label as a CSV file, and then you can check my this blog which focus on machine learning classification into the local environment and computer. You can check the blog right here, which shows how you can use scikit-learn and rastrio for the classification. So using these two workflows, you can do machine learning classification. You can use machine learning model for nearly any task using either completely Earth Engine, or you can use a hybrid workflow. So this was all for the workshop. And if you have any kind of question, you or issues with the code or the samples, you can navigate to this project repo. And in the issues section, you can find this button, new issue. You can create the new issue if you found any bug or suggestion. Or in general, if you need help, you can contact me on my LinkedIn. You can go to my web page and you can find my LinkedIn here. And yeah, so see you in another workshop. Bye.